Hi everyone, how are you doing? Okay, so let's get started. So let's do few questions which we have kept as an homework in the lectures of linear transformation and change of basis. So let's do those questions as well as the summary that what we have seen so far. Okay, so let's just get started. So whatever we have discussed, so we will discuss the summary about it, and then we will also do the questions. Okay. So suppose that you have a vector x, then what you can do, you can represent this vector x into multiple bases. So can you tell me what are the possible bases? One of the very popular bases is standard basis, and there could be some other bases also in which you want to represent, right? Maybe basis two, basis three, like this. Okay. Now, some of you might be thinking, first of all, that why we need multiple bases. I mean, why we need to represent a vector x into multiple bases. Okay, so you will get to answer this in the similar matrices, SVD, and these kind of topics. Okay, but first let's just quickly revise that how to change the bases. Now, suppose that we have a vector 2 3. Okay, this is a vector 2 3. Now suppose you want to change this basis. Okay, I mean these coordinates are with respect to our the standard basis, but now let's suppose that there is some other basis which is 1 2 0 3, and we want to change the basis of the vector 2 3. So which means what we can do, we can represent this vector 2 3 with respect to this 1 2 and 0 3, and whatever the number that we are going to get, we will be representing this 2 3 in that terms, which means I think 2 3 will be 2 into minus 1 by 3 into this, right? So with respect to standard basis, the coordinates are 2 3, but with respect to this basis, right, the coordinates are 2 and minus 1 by 3, right? Everyone knows this. Okay, now let's just move to quickly uh, the other slides. So basically, let's suppose you want to change the basis. Now, what we can do, let's just see that how to change the basis. For example, that if you want to change the basis from standard basis to some other basis, so how to change the basis? Let's just quickly see this, right? So change. Now, what we can do? Let's suppose there is a vector v. Okay, there is a vector v, and with respect to standard basis, there is some coordinates. Now, let's suppose the new basis. Okay, the new basis is b1, b2, b3. Suppose new basis is b1, b2, b3. By the way, quiz is ready. Okay, so there will be 25 marks quiz, and I think there are 16 questions. Okay, and I think if I remember, then there are 9 questions of 2 marks, and there are I think the remaining questions, which are 7 questions, right? Questions of 1 mark. Okay, so I was thinking that we can have 1 hour, okay, for this quiz. The reason is that generally, if there are 16 questions, then it should be around 45 minutes. It should be around 45 minutes. But I'm giving you 1 hour. The reason is that it is a very first quiz of this kind, and the sometimes the calculation are little lengthy. I mean, in most of the questions, calculation might be little lengthy. So, for example, you might need to find a inverse and these things, right? So that is why I have kept it for 1 hour instead of 45 minutes. I mean, for 16 questions, it should be approximately, for each question, it should be approximately 3 minutes, right? For some questions, lesser than 3 minutes. So that's why it should be 45 minutes. But still, I have kept it 1 hour. Okay, cool. So it will be just uploaded in 2 3 hours. Okay, by tonight only, and so that you will be able to attempt. So suppose there is a new basis which is v1, v2, v3. Now there is a vector v, and I want to represent this vector v in this basis. So what we can do? Which means the idea is that we want to get C1, C2, C3, right? We want to get C1, C2, C3. Now, first tell me, if V is a vector, V1, V2, V3 are the vectors, then this C1, C2, C3 are vectors or scalar? Tell me. These are scalars, right? Okay. So C1, C2, C3 are scalars. And our goal is to get C1, C2, C3. So how to get C1, C2, C3? We will be doing something like this. So it will be B1. Okay, Preetham is asking when will probability will start. I think it will take one more week. Okay, for probability. This is V, which is equal to this one, right? Now you tell me, if you want to get the C1, C2, C3, then how you can get the C1, C2, C3? You need to multiply by, let's suppose this is a matrix B. You need to multiply by B inverse. So finally, the new coordinates, which are C1, C2, C3, are B inverse V. So you can say that if you want to represent in new basis, okay, then you need to multiply by that B inverse. So for example, if B is in the standard basis and this BB is in the new basis, right? In basis B. Then suppose I say that what is the relation between B and VB? Then what you will say? V equal to BB multiplied by B, isn't it? Do you remember this? That if you have any vector in any basis, you multiply by the basis, then you will be getting the standard. I mean the coordinates in the standard basis. Do you remember this? And that's what we have just stabilized. So which means that if you want to get this, then it will be B inverse B. It will be B inverse B, right? Okay. So this is what everyone knows. Now, let's just see that how we can convert from any arbitrary basis B1 to any other arbitrary basis B2. Okay, B1 to B2. What I mean to say that the input vector X is in B1, and what should be the relation between X and B2, between these two? Or maybe in other words, let me write B2 here, because I will starting with B1 and ultimately I need to get B2. So let me write B1 on the right hand side and B2 on the left hand side. Just tell me what is the relationship between these two? What should I write such that the whole thing is in B2? Is this correct? Is this correct? No, right? This is not correct. So what is the answer? It will be B1. If you multiply by B1, then it will be in the standard basis. And then multiply by B2 inverse, it will be in the new basis, which is B2. Okay, great. So basically, whenever you multiply by B2 inverse, then it means you're changing that particular thing into the basis of B2. Okay. So this is the matrix that you're getting. Okay. This is the matrix which changes any vector from, I mean, the coordinate should be in the B1. It changes any vector which is in the coordinate of B1 to the vector in the coordinate of basis B2. Okay. So I think this is something we have discussed in this particular lecture. Okay. So for example, if this is a question, find the change of basis matrix from standard basis S, and use this matrix to find this particular representation. So they are saying that if let's suppose this is a vector space and this is some basis, okay, then change of basis matrix from standard basis to this basis. Then what you will do? From standard basis, which means given the vector in the standard basis, you want to get into this basis. You will be multiplying by S or you will be multiplying by S inverse. Just let me know. You will multiplying by S or S inverse. Yes, you will multiplying by S inverse, right? Okay. You need to find S inverse and then you will getting your answer. Okay. So for example, if this is the basis, then you want to represent this particular 1, 2, 3 in this basis. How you will be doing it? So 1, 2, 3 you want to represent that 1, 2, 3 in the new basis. You will multiplying by T or you will multiplying by T inverse. So what do I mean to say is that So what you will do here, if this is the kind of thing, then you will say that, okay, the relationship between 1, 2, 3, right? Okay, 1, 2, 3 in T and 1, 2, 3 normally is basically, you can say it is something like this. You will be multiplying by T, right? Here you will be multiplying by T. So that's how we remember it, right? You will multiplying by T here. Now, this T into this is this 1, 2, 3, and you want to get this. You have this, which is just 1, 2, 3. You will multiply by T inverse, right? So your answer is T inverse 1, 2, 3, right? This is your answer. Okay. That's an easy question. So I hope you understood it. Okay. So we will see this diagonalization a little later. Now let's just go to this. Just tell me if this particular question is okay, which means they are saying it is a basis. Then if you want the basis vector in that basis itself, then it is 1, 0, and this vector is 0, 1. Understood what they're asking? You take any arbitrary basis b1, b2, and then they are saying that you want to represent this b1 with respect to its own basis, then it is 1, 0, right? Okay, that's what you already know. Understood, right? Okay, so this is true. Now let's see this question quickly. What they are saying: let b and c be the basis. Find the change of matrix which can change from b to c and c to b, right? And v is this with respect to standard basis. Find its coordinate in b and c. So they are asking two matrices. One matrix which can change from b to c, and another matrix which can change from c to b. So they are asking both the matrices. So now you tell me what is this first matrix in terms of b and c? C inverse b, b inverse c, something like this. Yeah, the first matrix will be c inverse b. Yes, and the second matrix will be, you take that inverse b inverse c, right? Okay. Now, interestingly, tell me if this is the vector you want to represent in the basis b, then then what you will be doing? You will be multiplying by the first matrix, second matrix, or what you will be multiplying? Yeah, you will be multiplying this b with the b inverse only, right? And here with the c inverse. Okay. Yes. I hope that is fine to everyone. I think this is easy enough, so that's why I'm not writing it, right? Or should I explain by writing it? Let me quickly know if there is any doubt here. Okay. See, I hope you guys understood, but still, quickly let me just tell you that if these are the matrices that you have, which is if you want to go from B to C, which they are calling uh, MBC, something like this, right? If you want to go from B to C, then basically what you will be doing, any vector which in the basis B, then you will let's suppose you're converting to the standard basis, and from standard basis you are going to this. So C inverse B. Okay. So C inverse is the B is the matrix which can go from input basis B. So here the multiplication should be this, right? And then finally, so you can say that if you want to represent this in C, given that this is already in B, then you will be multiplying by C inverse B, right? Tell me, is this relationship correct or not? Is this particular relationship correct or not? If you have, if you have, let's suppose in the standard basis, and you want to get into the, let's suppose, basis of C, then will you be multiplying C inverse B? Will you be multiplying C inverse B? No, right? No. So this is wrong. So basically, you will multiplying C inverse B only when the input is in the basis of B. Okay. Otherwise, you will not be multiplying. Okay. Cool. Let's just go to the next thing. Let's just quickly solve this. Okay. Have you people tried it? Let me know. So in this question, what they are saying that you have this particular basis. Find the change of basis that can convert from B to standard basis. Okay, change that can convert the coordinates in B to standard basis. So you will be multiplying by B directly, right? So you will be multiplying by the B. So this is the answer. I mean this is the same answer. And if you want to get reverse, then you can take the inverse of that matrix. Now they're saying let X be this. Compute X in the standard in the basis B. Then what you will be doing? You will be multiplying by B inverse or B? B inverse, right? Yes. Okay, cool. Now, yeah, it was a good question. How many of you were able to solve this? So what they're saying, the two bases are given, right? Now let me just tell you one thing here. That let's suppose you want to convert from basis B1 or maybe basis B to basis C, right? So basically, what is the matrix that you are multiplying? You are multiplying this, right? This is the matrix, the desired matrix. Can I also say, let's suppose this is having B1, B2 vectors. Okay. Can I also say this is same as C inverse B1, B2? And if you multiply a vector by C inverse, okay, and the vector is in the standard basis. I mean, this vector B1 itself is just like a standard basis, right? Standard, I mean, represented in the standard basis. So can I just say it is nothing but coordinates of B1, coordinates of B1 in C, coordinates of B1 in C, and coordinates of B2 in C, जो भी input basis है, input basis you will be writing here, and the coordinates of input basis with respect to other basis. Can you say something like this? So basically, the matrix either you write like this, which means C inverse B, or maybe you can also say that okay, coordinates of input basis with respect to the other basis, output basis. Now let's just see this question. Okay, now let's just see this question. So now what they are saying is very interesting. Let's just try to see that how to solve this particular question. Okay. So they are saying that this is a vector v1, this is a vector w1, and this is a basis vector. These are also basis vector. So you want to change from the basis with respect to basis v. So you want to go from basis b to basis w. Okay. So what is the output basis w, and what is the input basis this? So what is the answer? Can you tell me the answer in terms of the shortcut notation that I just told you? Can you tell me the answer? So the answer will be, okay, if you like to tell me the answer, then the final answer will be that can convert the input basis to the output basis W. What is that answer? It is V1, V2, V3, and then this is W1, this is W2, this is W3. Is this okay to everyone? Let me know. This is the matrix which will be converting from the basis B to basis W. Isn't it? Let me know if that is fine. Yes. Right? So now you tell me, do you have answer directly? So what is the representation? Okay. It should be W instead of W1 W. Yeah, sorry, it should be W. Yeah. I mean, with respect to the basis W. Yeah. Okay. So now what is the answer? With respect to basis W, I think this is 4 minus 1 and 1. So this vector is 4 minus 1 and 1. And then this is 3, 2 minus 1. This is 7, 23 minus 2. Right? Okay. So this is how you will be getting. Now you tell me, can can you solve this question in any other way? Let's suppose you don't know that, okay, change of basis matrix will look like this. Can you solve this particular question in any other way? You don't have the values of v1 v2 v3, right? You only have the relationship between v1 v2 v3 and w1 w2 w3, which means that since you don't have that, what is the absolute value of v1, what is the absolute value of v2, what is the absolute value of v3? Okay, you don't have this. I mean, you have the relationship. You don't know what is v1, you don't know what is v2, you don't know what is v3, right? You don't know about it. You just know the relationship between that. Then in that case, can you calculate this W inverse? If you don't even know what is W1, if you don't even know what is W2, if you don't even know what is W3, yes, you know the relationship, but you don't know what are those exact values. Can you do this? No, right? So basically for these kind of questions, if you just have the relationship, so I think this particular shortcut method is very good. Now let's suppose they ask you that here, what is the change of matrix from V to W? And then also they also ask you, what is the change of matrix from W to V? Then what is the answer? From W to V. Then the input is W now this time, right? So it should be W1, W2, W3, and then V1, V2, I mean, sorry, this is in terms of V, this is in terms of V, this is also in terms of V. Okay. So can you, is this by the way easy to find out W1 with respect to V? Or it is easier to find out V1 with respect to W? See, V1 with respect to W is very clear. 4 minus 1, 3, like this, right? So you already know this matrix. But if they ask you this matrix, then yes. So it will be inverse of, okay? So you can take the inverse of, right? Okay. So this was a very good question to tell you that if they give you the relationship, then how to solve this question. How many of you were able to solve this question after this particular lecture? After this lecture number, okay, how many of you were able to solve? Just let me know. Okay, yeah, it will be difficult, right? It is difficult without knowing the concept of this. Okay, without knowing this concept, I mean, this particular concept, it will be difficult. This is very important. Okay, okay. Now let's just move to the next slide. Let's see that what we have studied. Okay, so I think these kind of things you can do. That's fine. Okay. Now let's just move to the next slide. Let's see what was there. I think in this particular slide we have introduced linear transformation, right? Okay. So what is a linear transformation? It is something with respect to, you can say that it takes a vector and do some linear addition or something, right? So for example, if you have some vector and then if you multiply by 5, okay, now, I mean, if you multiply by 5 before the linear transformation or you multiply by the 5 after the linear transformation, both are same. I mean, before this function, if you multiply by 5 and then do this linear transformation, or you first multiply by, I mean, you first take the transformation and then you multiply by 5, then both are same, basically, right? So basically, these are the two main rule of linear transformation, that how to perform the linear transformation, or which functions are eligible to call linear transformation. So the functions which are satisfying these two property are eligible to call linear transformation. What will the linear transformation of 0? The vector 0, it will always be 0. Okay, 0 doesn't change in the linear transformation. Tell me, is this a possible, is this a valid linear transformation? For example, I don't even tell you, okay, I don't even tell you um, the format of linear transformation. But if I say there is some transformation which takes a vector space V, any vector it takes in the vector space V, and it give you the zero vector. Okay, this is zero vector. Is this valid linear transformation? Or maybe I can say, is this transformation linear transformation? Tell me, what do you think? Is this transformation linear transformation? Just think about it. So I can say that this is a very dumb linear transformation. Basically, it is a linear transformation, and it is very dumb in the sense that it sends every vector to the zero vector, right? Why it is a linear transformation? Because there is a corresponding matrix. And what is that matrix? The matrix associated, okay? Let me just tell you. The matrix associated with this transformation is zero matrix. ठीक है? Why that is the case? Because you take any vector, and ultimately, if it is mapping to zero, then zero matrix will serve that purpose, right? For every vector, if it is sending to zero, then zero matrix will serve that purpose. So yeah, this is a very valid linear transformation, but you can say it is a dumb. Okay, it is a dumb linear transformation. I mean, it is doing very nice thing. It is a dumb. Got it? Okay. Now you tell me this. Now you tell me this. Let's suppose the transformation from any vector space V, it is sending to, okay, 1 1 1. Is this a linear transformation? See, if there is any constant other than zero, then it is not a linear transformation, right? Then it is not a linear transformation. You can easily guess why. Because if you first multiply any, any particular vector, let's suppose if you 2 3 4, if you take this, right? If you first multiply, then it will be just 1 1 1. But if you multiply later on, then it will be 2 2 2, right? Yeah, and this is Gaurav is also saying very nice point, because transformation of zero is not zero. Transformation of zero should always be zero in linear transformation, right? So that's why I can say this is not a linear transformation. Okay, okay. Now you just tell me this: is this a linear transformation? Is this a linear transformation? The answer is no, right? This is not a linear transformation. We have seen these things before. You just tell me this, okay? Instead of this one, let's suppose I have zero. Only change I did it that earlier it was one, now it is zero. You tell me, is this a linear transformation? See, if we have 0 as a constant, then it doesn't really matter, okay? Then it is not violating the property, okay? Then it is a linear transformation. Otherwise, if there is any other constant, for example, 1, then it is not a linear transformation, okay? Cool. So let's just see it more. So I think we have given couple of examples of linear transformation, these things. So hopefully that is fine. Yeah. Now, now we have very interesting theorem, which is that every matrix multiplication is just a linear transformation, and vice versa. Okay. So this slide is very important in that sense, that every matrix multiplication is a linear transformation, and every linear transformation has associated matrix. Okay. So so it is both ways. Okay. If you have linear transformation, then there is a matrix multiplication associated. There is a matrix associated with that. If if there is a matrix multiplication, then it means it is a linear transformation. Okay. It is both ways true. Okay. So how to find that matrix? How to find that matrix? Let's suppose this is something that linear transformation is given to us, and I want to find the associated matrix with this. Then what will I do? So I can do one thing. Let's suppose this is given to me, right? Okay. So what I'm ultimately looking for is something like this. Let me just tell you what I'm ultimately looking for. See, ultimately I'm looking for something like this. That let's suppose there's a matrix. Okay, I'm looking for a matrix A. Let's suppose there's a matrix A. Then I'm looking for something like this. T of x y you do, or A into x y you do. Both are same, right? So we want to find A such that it satisfies something like this. Okay. So what is A here? Now, what was the trick that we have played to find out A? So we said, yeah. So we said that we can put, instead of this xy, okay, it could be anything, right? Instead of this xy, let's just put even first. Then it will be T of even equal to A of even. A of even is nothing but, if A is A1 A2, if A is A1 A2, then A of even is A1 or A2. Tell me, it is A1, right? It will be A1. So finally, we found out that A1 is nothing but T of even. Okay. So this A1 is nothing but T of even. So this was the trick that we have played. That okay, let's just put even, and we eventually got A1. Similarly, instead of this xy, we can put E2. Okay. And we will be getting A2. So that is how we constructed A. So what is the final A? See, A1 is sorry, A2 is TE2, A1 is TE1. So that is why the finally A we are getting is something like this. TE1, TE2. This is the standard matrix with respect to this transformation, right? T. Okay. So I think these things are fine. Now, okay, let's just see this, which we have given as an homework, right? Okay, let's just see this particular question. How many of you had solved this question? Anyone who tried to solve this question? I mean, you might not be able to solve, that's fine. But anyone who has tried? Okay. So you people have not even tried. Don't do these kind of things. Just try the questions, right? Otherwise, you will be getting less marks in the quiz. So if you don't try the questions, you will not be getting good marks in the quiz. Okay, because quiz for the quiz you should be trying the homework questions at least. So let's just see this question. What they're saying? They're saying that suppose A is 7 cross 5 matrix and the null space of A is a line, which means the nullity of A, nullity is how much? If it is just a line, then nullity is how much? Yes, 1, right? Nullity is 1. If it is just a line, then nullity is 1. Say that T is matrix transformation, which of the following statement must be true about the range of T? Okay. So, okay, I think we solve this question in the next lecture. Is this? Okay. So what is the range? Range means that the column space, right? So range means you can say the dimension of column space. Okay. I mean the column space basically. So if nullity is one, number of um columns are five. So column space dimension is four, right? So range is a four dimensional space. So either A is answer or B is answer. Now tell me it is in R7 or R5? Columns are, since there's 7 rows, so it is in R7, right? So columns are of 7 dimension. Okay. So it is in R7. So I think A is the correct answer here. Okay. Now let's see what we have seen in the next lecture. So here we have seen more on linear transformation. Okay. So we have seen these things. Great. Yeah. So for every linear transformation, there is a matrix. For every matrix, there is a linear transformation. Okay. Uh, so this particular slide I've taken from this university, and I've told you multiple times. It is a both way. Okay. If it is a linear transformation, then it is a matrix. If it is a matrix, then there is a linear transformation associated with this. Okay. Find the standard matrix for this. So how to find the standard matrix? Can you tell me what is the answer here? The given vectors. Let's suppose this is b1, b2, b3. So the given vectors are the answer itself, right? Given vectors are the answer itself. Okay. Yeah. Let's just do this question. Okay. I have solved it next. So anyway, so let's just see this. So what is the answer here? T1 is minus of E1. T2 is this one, right? So it is just you can say that minus of E1 you can calculate, and E2 minus 2 E2 you can calculate, and you will be getting this, right? Okay. Or maybe you can consider this as a, the coordinates in the standard basis will be minus 1 of E1, so and 0 of E2. So minus 1, 0. Here, minus 2 and 1. Minus 2 of E1, which means minus 2 is the first coordinate, and the second coordinate is 1. Okay, so this is okay. Yeah, let's just see this. If we have two linear transformations, then if you want to find out the composition of linear transformation, then also it is easy, right? What you need to do, you need to multiply by the matrices associated with that. Okay, it is very easy to find the composite linear transformation basically. Okay, we did these kind of easy questions. Okay. Now we have understood that what is relationship of this linear transformation, or what is the similarity between linear transformation and the functions. So which means ultimately linear transformation is just a function, right? So what is the similarity? Basically, you will be saying that the linear transformation, whatever you have, is just a function. So we can use the function terminology. For example, we can use map, domain, codomain, image, or range, or these things, right? So domain, this is called codomain. And whatever the subpart of this codomain, it is called range. Okay. And here, in terms of linear transformation, the range will be the column space. Okay, column space of the associated matrix. So this will be the range, column space of the associated matrix. Now let's just see. Now let's just see what is onto, what is what is one to one function, what is onto function. So one to one function says that uh, for example, let's suppose this is some value 3. Now this will be mapped only to one of the value. For example, see here, this is not one to one function because these two values are mapping to 3. So now I think we have done examples on the next slide. See, this is a one to one function. In the one to one function, some of the part may get leave. Okay, that's fine. But if it is 1, then it has to map to 1, which means this cannot be mapped to 2. Which means that what I'm trying to say here is that if you have something like this, okay, something like this. First tell me, can this be mapped to 2? Can this be mapped to 2? In any function, is this possible to have two possibility for just one input? No, right? So this we have taken care by the definition of the function. In one to one function, we are taking care this, that okay, that this will also not be mapped to some other value. For example, if I just say this, see, if I just say this is not even function, right? Now, if I say this, that okay, this I am taking care. I mean, as a definition of function, this will not be mapped to two things, but this can still be mapped to two things, right? Something like this. Is this a function? Tell me. Is the part B a function? Yes, it is a function, right? So it is a function. For example, it could be the function of x square, where -2 and 2 both are mapping to 4, right? It is definitely a function. Let's suppose x square. But it is not a one-to-one function, okay? If it is mapping, see, this cannot anyway map, but if this is mapping to two things, then you will say it is not one-to-one function, right? Okay. Now tell me, tell me, see, I cannot map this to two, that's fine, okay? And I cannot map, let's suppose I don't want to map this to two, which means everyone here by definition I have to map, right? So everyone here I have to map to something, right? So for example, this, and let's suppose there are some more elements, right? Tell me, is this a one-to-one function? Yes, it is one-to-one function. Okay. Is this fine to everyone? What we are trying to say, that you can leave out anything here, but one thing cannot be mapped to two things, right? So for one-to-one function, what you need to do, see this kind of a structure will be one-to-one function. The only extra thing can come on left hand side or right hand side. Tell me, this kind of a structure will be one-to-one function, but the extra thing will be coming on the right hand side here. Here, this could be extra thing. Okay, so this is one-to-one function. Understood? Okay. And now let's just see what is on-to function. Okay, this is one-to-one function. Okay, I think, yeah, here are the definitions. Now let's just see what is on-to function. What is on-to function? Can anyone tell me? In on-to function, it says yes, the codomain and range are same. It says that, see, in the function definition itself, you won't be leaving anything from the left hand side. You can leave till now. You can leave from the right hand side, but onto says that there is no possibility that you can leave on the right hand side also. Okay, so this will be mapping to this. Okay, this can map to I mean, this has to map to something else, because it is a function. This cannot map to the same thing. So anyway, so it will be mapping to this, it will be mapping this, and here you have to have something else. So basically in the onto, you will be mapping everything here to something here, right? Okay. Is this possible that this particular any output can be mapped to two things here? Yes, this is possible, right? I mean, in the onto, it is definitely possible that this is mapped to two things, but you will not be leaving out anything here. This is called onto function. Okay. Now, now, if it is onto and one to, this is called bijection. Okay. See, bijection function are that which is one to one and onto. Which means, what does one to one says? The architecture of one to one, as you remember, it is something like this, right? You may leave out something here, but since it is onto also, you cannot leave out something here. So that's why if it is perfect matching, okay, if it is perfect, then it is called bijective function. Okay. Anyway, these are the definitions. Now let's just see some questions. Okay, and then you can quickly recall. Do you remember this question? Okay, let's just okay, just tell me ABCD, whether age of one to one, on to, neither, both, something like this. A is, I think, one to one function, right? What about B? B also seems like one to one. Is it? See, this is mapped to this. That's fine. That's fine. That's fine. Yeah. B is also seeming like one to one function. Tell me. No. Right? Because this two is mapped to two things. So it is not one to one. But since nothing is getting left out here, so that's why that is on to. So it is on to. This is one to one. Since nothing is getting left out, this is on to. And only, one incoming arrow. So this is one to one. One to one and on to both. It is not on to. Is this one to one? Yeah, I think this is one. No, this is not on two. This is neither one to one, because this two is having two incoming arrows, and this one is not even a function, right? Okay, so this is the answer. Yeah, great. Now let's just move to the next slide quickly. Now suppose you want to find out domain, codomain. Then what is the domain? Domain will be a vector in R2, right? A vector in R2. So basically domain is R2. Codomain is basically just 3. I mean, it will be R3. And most interestingly, what is the range? It is the column space, okay? It is the column space, and you can find out T01. So range is nothing but the column space of A, which is the span of these two vectors. Okay. Now let's just see what is one-to-one transformation. Okay. I mean, functions we have seen, but in the similar terms, let's just see what is a one-to-one transformation. So it should be, linear form. I mean, one-to-one. So it means if there is a x, then, or maybe in other words, if there is a b, then there is corresponding just one x. Okay. So basically tx equal to b has at most one solution. It may be zero solution also, but at most one solution, right? I mean, some of the things may get leave out. So here, this is basically x. Any vector here we are calling x. Any vector here we are calling b. Okay. So for every b, there is at most one x. Okay, at most one x. There may be some b which is leaving out. That's fine. So it is called one to one. If tx equal to b has at most one solution. Okay. So which means if there is a B, then if it is having two solution, not one to one, if just having one solution, or maybe no solution, then it is one to one. Which means at most one solution means column space of A. It is or sorry, columns of A should be linearly independent. This is very important to note. The columns of A should be linearly independent. Okay. So let's just move to the next slides. Is this one to one? Is this function one to one? How to identify one to one? It should be having for any b, it should be having at most one solution, which means column should be linearly independent. So is the columns linearly independent? Yes. So that is why this is one to one. Okay. This is definitely one to one function. Let me know if there is I mean everything is fine till now. Okay. It is fine that this is a one to one function. Why? Because do you remember that if you want at most one solution, then for ax equal to b, if you want at most one solution, then columns will be must be or should be linearly independent, right? If you want, let's suppose exactly one solution, then in that case, columns should be linearly independent. What else? Plus, plus, what else? Columns should span, right? Should span, uh, you can say basically the whole codomain, right? Okay. Is this one to one? Columns are not linearly independent, so you can say no, it is not one to one, right? And what is the onto transformation? Onto means that you should not be leaving out, right? Which means for every b there is a solution. So it means at least one solution should be there. Okay. So you're not leaving out anything. So that's why you will say that at least one solution. So for onto, you will say at least one solution. which means that for every b, you're not leaving out anything, any b. So there will be at least one solution. There may be multiple solutions, but at least one solution will be there for every b. Okay. Maybe just one solution also. For example, if this is b, then maybe just one solution also. That's fine. Okay. Maybe just one. That's fine. Okay. So this t is on to. Tell me, for on to you must be having solution for all the b's. It is spanning R2. Will you be having the solution for all the b's? I think yes, right? I think yes. So that's why it is on to. Okay. Easy question. It is on to. Okay. So I think these are okay. Let's just quickly see this. Do I have the, yeah. So suppose this is the final matrix that they are getting after the linear transformation. Oh, sorry, after the row transformations. So this was the question. Okay. Tell me. Uh, one, two, three. Yeah, this is the matrix. Tell me, is this on to, is this one to one? What is the answer here? Let's suppose this is the matrix we are getting. So on to means you will be having solution for everything. This is one, two, three pivot, right? Okay. In R3, you have three linearly independent. So I think yes. So it is on to. One to one means you will be having at most one solution, basically, right? But here you will not be having at most one solution. So on to but not one to one. So C is the answer here. Okay. Because this is a free variable. That is why you will not be having at most one. Okay. You will be having multiple solutions. So that's why C is the correct answer here. Okay. Okay. Maybe we can try this. Or maybe you might have tried it. Let's just try something, some other question. Okay. Do you want to try this? Have you tried this question? By the way, is this a linear transformation? They are having zero. They are having constant. Is this a linear transformation? Yes. This is a linear transformation, right? So, what they are saying, that is on to one to one like this. So, if you have this, maybe you can find out the standard matrix. This is not on to, since this is not in the range. Yeah, sorry. By looking at this directly, you can say this is not on to, right? Because for every b there is not a solution, because it is fixing zero. Okay, for every b there is not a solution. So this is not on to. Is this one to one? What do you think? I think it is not even one to one. Why? Because it is possible that, let's suppose, the moment you keep x and y same, right? X and y same, and z, maybe you keep on wearing z, doesn't really matter. Sorry, you fix z, and then you keep on wearing xy such that x and y are same. So it will be 0 0 0, and let's suppose it is 5. So 0 0 0 5 is mapping to many vectors here, right? So what I'm saying here is that it is not even one to one. Okay. So can you give me the example where one vector on the right hand side, maybe you keep something like this, okay? Something like this. One vector on the right hand side, 0 0 0, let's suppose 5. Okay. This is the answer of many different vectors on the left hand side. For example, the moment you keep x and y same, z5, then this is also mapping to 0 0 5. The moment you keep x and y same and z as 5, this is also mapping to this, right? So that's why this particular vector is mapping to two vectors, or maybe multiple vectors. So that is why it is not even one to one. It is not onto, because onto should cover everything on the right hand side, but it is covering only the vectors which is having the first dimension as 0. So C is the correct answer, right? T is not one to one, right? So Ajay is saying that Tx equal to, Hers is saying Tx equal to 0 has non-trivial solution. Yeah, that's also good example. Tx equal to 0. If you have all the zeros, yeah, that's also fine. That then it is also having non-trivial solution. Yeah. Now let's just see this question. What they're saying, say that S and T are the linear transformation. Which following must be the true about the composition? Okay. So maybe let me just copy this on the next slide. So by the way, is the composition defined? So S will give the output in R3 and T will have the output in R3. So a composition is defined. And this T composition with S, this will be in the T is taking from R3. So I think, uh, see, let me go to the slide after, pasting on the slide itself. Okay. What they're saying is that this is T composition of S, right? Then S will take something from R2. So which means this X, whatever they are taking, it is from R2, right? So input is from R2, they will be taking. Then it will be giving in R3. It will be taking from R3 and it will be giving in R4. So this T composition of S, it is from R2 to R4. Okay, it is from R2 to R4. Now let's just see this. Can this be one to one? Can this be one to one? Just think about it. See, if you have any transformation, maybe U from R2 to R4, then what does this mean? Can you write the matrix corresponding to it? The dimension of the matrix, can you tell me? It will be taking from R2, giving in the R4, right? So 4 cross 2, which means 4 rows and 2 columns only. So this is the matrix corresponding to it. Okay. This is the matrix corresponding to it. Can this be onto, by the way? Can this be onto? See, by the dimension itself, okay, by the dimension itself, we can say it cannot be onto. Why? Because you are having an R4, okay, in R4 you are just having two. So you won't be able to fill the space. So never onto. So onto cannot be there. Can it be one to one? Yes, it may be linearly independent, right? So you can say it is one to one. It need not to be. It can be. It can be one to one. Composition is actually defined. It is onto. No, it is not onto. So it is not onto. It's for sure. Okay, cannot be onto. It is not one to one. Is this always true? Is this always true? It is not one to one. See, about one to one, you can't say. Maybe one to one, may not be one to one. It will depend whether the columns are linearly independent or not linearly independent, right? It will depend on the actual transformation. But while looking at this dimension itself, we can say it cannot be onto. Okay. If it is from 2 to 4, so if a transformation, let's suppose T1 is from R2 to R4, then then the matrix associated with this will be from 4 to 2. This is a matrix. So which means two columns in R4. Okay. Then it cannot be onto. It cannot fill the space. What about what about uh, the transformation? Let's suppose R4 to R2. So what is the matrix dimension? 2 cross 4, which means there will be four vectors each in R2. Now tell me, can it be onto? Can it fill the space? It can be onto. Can it be one to one? Because columns must be linearly dependent. Okay. So by looking at the dimension, I can reject one of the possibility that it cannot be onto, it cannot be one to one like that, right? If the dimensions are different, if the dimension, let's suppose, are same, for example, let's suppose I have 3 cross 3. Now, can I say it is on to, it is not on to, it is not one to one, something like this? By looking at the dimension, can you infer anything? Can you say it is not on to, which means that it is not filling the space? I cannot say, because maybe it is filling the space. If columns are linearly independent, maybe it is filling the space, right? So it may be on to, it may not be on to. Can it be one to one? It depends. If columns are linearly independent, then it is one to one. If it is not, then it is not one to one. So if the dimension is same, I can't infer, right? Now I can't infer. Just looking at the dimension, I can't infer here. But in these two cases, just looking at the dimension, I can infer something. Okay. Is this fine to everyone? So that is what I think they are trying to convey, okay, in this particular question. Okay. Now let's just see this question quickly. Let's just see what they're trying to ask in this question. Just give it a try. Let me just wait for 1 minute. You just give it a try. So this is a theoretical question, by the way. So let me just tell you what they are trying to say. How many rows and columns does A have? So if it is, going from N to M, then A will be, tell me, M cross N, okay? M cross N. X is in Rn. How do you find Tx? Tx is just Ax, okay? In terms of A, how do you know T is one to one or onto? So if you know that if columns of A, okay, if columns of A are linearly independent, it means there will be at most one solution, right? So you can say one to one. If columns of A are linearly independent, then one to one, right? And how we can say on to? If columns of A span Rm, right? Then on to. What is the range? Range is nothing but column space of A. Okay. This is just a theoretical question. Okay. So now let's just see this particular question. This seeming to be interesting question in the sense that okay, there is a solution. Okay. Yeah. It is easy and interesting, I think, right? Can you just tell me whether it is true or false? Just let me know quickly. Okay. So let's just see this. So what they are saying is that if T1 equal to T2, it means in the A, okay, if you remember the A, it will be T1, it will be T2 like this, right? If both are same, which means columns are linearly dependent. If there are linearly dependent columns, then for Tx equal to 0 or for Ax equal to 0, yes, there will be infinitely many solutions, right? If columns are linearly dependent, then there will be trivial solution. So this is true. If it is 1 to 1, okay, and M is not equal to N, T must not be on 2. Yeah, that's interesting. So they are saying that if it is M cross N matrix, it is 1 to 1 means columns are linearly independent. Okay. And M is not equal to N. Then it cannot span the whole Rm, which means that it is not onto, which is true, right? So this is also true. It was a nice question, I think. So basically, you can take the values of Mn and let me just explain that what they are saying. Let's just take instead of Mn, let's just take it to be maybe 4 rows and 3 columns. Okay, let's suppose 4 rows and 3 columns, just for the sake of example. If that is in R4, okay, if that is in R4, that is in R4, which means these are linearly independent columns. You can't take that in R2. If you take that in R2, will these 3 columns be linearly independent? No, right? Okay, so let's just take it in R4. In that case, three vectors in R4 will not be filling the whole space. So hence, it is not onto. Okay. So yeah, both are true basically. So this is true. This is also true. Tell me, is this a onto linear transformation? Tell me, is this a onto linear transformation? You should be able to quickly tell me for this particular question. The reason is that it is, yeah, it is not even the linear transformation. Yes, because this is one here, so that's why it is false. What about this? Then the transformation which standard matrix is A cannot be onto. If you have 3 rows and 4 columns, right? 4 vectors you have is in R3. They can fill the space. It can be onto, right? But cannot be 1 to 1. Can it be 1 to 1? No, it can be onto, but it cannot be 1 to 1. So this is false. Okay. Since they are saying cannot, okay, cannot be. It can be onto, okay. So that's why both are false, right? It is not even the linear transformation. It is false because it can be onto. So that's why both are false. Okay. Maybe this particular question you can try later on, right? Yeah. Is this easy or tough? They are saying it is onto. Then what you can say about the relative size of n and m? M is greater than or equal to n is greater than or equal to m, like that, right? So we have solved these kind of things just now, right? See, with the sizes also we can see. Okay, we have solved these kind of things. Okay, with the sizes also we can determine whether onto or not onto or something like this. So that's why you can solve this. Okay, you can solve this question. Okay, so these kind of questions, I think you can check once. Now maybe we can move to the next lecture slides. Okay, where we are going to discuss linear transformation with respect to some other bases. Okay, there might be input bases, there might be output bases also. Okay, let's just quickly see linear transformation with respect to other bases. So basically, what we want to do, let me just tell you that what we want to do. If we have any linear transformation, okay, T, then there will be some input basis and there will be some output basis. See, till now, what we have been saying that there is a matrix, okay, there is a matrix A which perform the task. But now people have been more greedy. They are saying that we will give you the input basis, let's suppose B1, we will give you the output basis B2. Now we are looking for some matrix, let's suppose M, such that it does multiple things. What it does is something like this. They are saying this matrix M takes takes X in my choice of basis. For example, B1 basis. This matrix M should be able to take X in my choice of basis, and then should be ultimately what I get is basically that it should be able to transform that vector X, and then ultimately I want the transform vector that too in the B2. Okay, so this is what is called linear transformation with respect to input basis and output basis B1 and B2. Okay, this is something we want to find out, right? Okay, do you want to give it a try? Then what is this M? Can you recall what was this M? Just give me a try that what is this M? Let's suppose this is A. Okay, the standard matrix is A. Then how to find out this M? So basically, you want a matrix that takes a vector in basis B1, right? Now what we can do to solve this? Okay, what we can do? We can say that let's just convert this vector X, which was in B1, maybe in the standard basis by multiplying by B1. And since this vector is in the standard basis, we know that how to do the linear transformation in the standard basis. Then this is the linear transform vector. Or you can say this is just Tx, right? This is a linear transform vector. Okay, this is Tx. And then you can change its basis again using B2 inverse. So this is the final basis that you have, right? This is the final basis matrix. Sorry, final matrix which you have. So the M is coming out to be B2 inverse A B 1. Let's suppose this B1 vectors, okay, are itself B1 B2. Then what you can say about this matrix multiplication particularly, you will be saying that this is nothing but B2 inverse. This is nothing but B2 inverse A into B1, right? A B1. This is A B2, which is nothing but this A B1 is nothing but T of B1. I mean transformation of B1. This is transformation of B2, and then it is getting multiplied by B2 inverse. Okay, and then finally you can say if you multiply something by B2 inverse, then this T B1 with respect to B2. This is T B2 with respect to B2, right? So if this is the input basis, B1, B2 is the input basis, then finally, the change of basis along with the linear transformation matrix M, which you are writing like B2 inverse A B1, which is same as if B1 is the input basis. So here T of B1, T of B2, And then this is with respect to B2. This is again with respect to B2. Is this fine? Let me know. Is this fine? Okay. So this is something we have discovered, right? That there are two ways to do the linear transformation with respect to input and output basis. See, there might be the questions in the quiz related to this, so you should be knowing that how to understand these two ways. So this is, I can say, two ways. Okay, to find the matrix which which does the linear transformation. I mean, which changes the so basically it takes the input from other basis B1, do the linear transformation, and gives the output from any other basis B2. Okay, B1, B2 I can choose. Okay, so we can choose B1, B2 to be any basis of our choice, right? Okay, so I think there were two methods. No, this is okay. Maybe I can go to the next lecture. This one. Okay. Okay, so there will be two bases, input basis and output basis. And how to find that matrix? We got to know that the matrix is this, right? Okay. Then I think we have done couple of questions to practice. For the practice purpose, we have done couple of questions where the input matrix and output matrix, these things were given. Okay. And using other method also, I think we did, and we verified that. Okay, using method one and method two, I think the way one do the transformation directly, way two use the final matrix. Okay, so we have done using two ways, and we have seen that that was working, right? I mean, the way one was saying that you do the transformation and then you change the basis to B2 manually. V2 was saying you use the final matrix directly. Okay, so yeah, using these two ways we did it. Now we have also seen that if there are multiple things which are given, for example, if they are saying that okay, from B to C change of basis is given, then linear transformation is given, then change of basis is given, then they're asking, let's suppose B to E or something like that, then we were able to do these kind of questions also, right? Are these kind of questions also fine to everyone? Okay, okay. So I think these are just more practice questions, and then we wanted to start this similar matrices. Okay, so in the lecture number 10, yeah, we did more questions, that's all, right? Okay, Bachu Paul is asking that, sir, I have one doubt. Yeah, you can unmute yourself and you can just let me know.
Yeah. Hello, sir.
Yeah, hi.
Yeah, hi, sir. So, sir, in one of the question, I'll just share the snapshot for this one.
Okay.
How can we solve for the, I just shared one snapshot. So, how can we
Okay.
solve for that B inverse for that basis vector?
It was in which lecture, by the way?
I think in the ninth,
Okay.
yeah, the part B.
So what they're saying, change of basis Rn and the subspace of Rn coordinates given basis as well as relationship between. Compute the coordinate transformation matrix B, that is compute the matrix W.
Yeah, A part is fine. B part has some doubt.
Got it. Okay. Just a second. Okay. Consider two bases, this B1 and B2. Compute the coordinate transformation matrix C such that it convert from B1 to B2 for all the y.
Yes, here we have to find the value of C.
Okay, okay. So you can use that formula, right? I mean, in the sense that you can find out the relationship between, let's suppose this is, so C will be, you can represent, what is the input basis?
B1 input
B1,
is
B1, right? So let's suppose this is U1, this is U2. So it will be U1 with respect to B2, U2 with respect to B2. So yeah, so you can solve this, that what is the coordinate of U1 with respect to B2. So you can represent this in terms of these two. So I think it is just a summation of these two, right? So
E.
one into this and one into this. So it will be 1, 1 and U2 this one. I think this is 1, this minus this. So it is 1 minus 1. Okay. So C will be something like this.
Okay. But sir, this U1, B2, this the one which we represented. So this one again leads to B2 inverse into B1, right? You have just proved in earlier classes.
Okay.
So this C equals to U1 with respect to base B2, U2 with respect to base B2. So this will ultimately leads to B2 inverse into B1.
Yeah, but if inverse doesn't exist, then we can't find the inverse. So, okay, I got a point. So you are saying that let's suppose that there is some vector x. You want that in terms of b, right?
Yes.
So it will be the standard vector x and then b inverse. Okay. So okay, I got a point. So basically, this is true only b inverse exists. Otherwise, I think we need to go with this way only. That this is what we know, that x is, now if we want some vector x in any other basis, right? Then, so what we will be doing, so we will be finding xb as, uh, so basically this is the coordinate of x with respect to b. So it is b1, just a second. So see, in this particular case, coordinate of u1, so this vector, okay, see, so if the inverse does not exist, then I think we need to just check the coordinates. So suppose here we want to find out coordinate of u1, this is u1, right? Coordinate of u1 with respect to b2. So what we did is u1, normally u1 equal to, so let's suppose this is v1, this is v2, something into v1 plus something into v2, right? These are the coordinates.
Yeah, it will be 1, 1. 1 into V1 plus 1
Right,
into V2.
right. Similarly here also. So if you want x in terms of b, okay, so you can't like write like this. Yeah, so maybe this formulation won't directly work. So in that case, you will be writing this x equal to same, I mean, in the standard format, this x will be something into the basis vectors b1 and b2. Then these are the coordinates of x with respect to b1, b2. Yeah, in that case, inverse, if inverse doesn't exist, then we have to go with this way, finding the solution of this linear equation. Okay.
Okay. So in that case, even let's say this B1, B2 bases are there, and if we represent U1 in terms of V1 and V2, then the resulting final U1 with respect to basis B2 will have
Yes.
five entries in that vector. Means U1 with respect to B2 should have five entries. Should be in R5.
Okay.
Yeah, U1
No, no. Uh, no. Basically, this U1, this vector with respect to this basis. No, since this is the only basis, so that is why it will be just two entries here, right? Just two entries. If this is the only basis, and yeah, it will be just two entries because number of basis vectors just two in this B2.
okay.
Yeah, that's interesting. So I will do one thing. Actually, this is related to pseudo inverse and these kind of things. So I will do one thing. When I tell you the left inverse, right inverse, pseudo inverse, these things, so I will bring this kind of thing again, and then I will try to relate these things with the pseudo inverse and left inverse, right inverse. Okay.
Okay, sir.
But for now, you can understand that if you can't find the inverse, then this is the way.
Okay.
Okay. Okay. Thank you.
Thank you, sir.
Okay, so we have one quiz that I think most probably it is uploaded now, or it will get uploaded tonight, and then you can attempt that quiz, right? Tomorrow we will be speeding up with the other topics, which is like similar matrices and these things, okay, and diagonalization, eigenvalue decomposition, and these things. So tomorrow we will be speeding up with similar matrices, diagonalization, and these other topics which are very important. Okay, so these things. Okay. So thank you everyone. Thank you so much. Take care.